This video will focus on, first of all, introducing the equation that relates to how to quantify heat for a temperature change situation, where we'll define what specific heat capacity is, and then also we'll focus on the 3 laws of thermodynamics that will allow us to understand how temperature change relates to enthalpy. So to begin with, we're looking at a new scenario where it's not a chemical reaction situation, but instead we just have something cooling up or heating down. And the question is, how do we quantify heat in this case when something is heating up or cooling down? And to calculate that, we need to know 3 different things about the substance. First of all, we need to know something called the specific heat capacity. And the specific heat capacity is the variable for it is C. And the specific heat capacity, by definition, is the amount of heat energy needed to take 1 gram of any substance and make it 1 degree hotter. And what's awesome about specific heat capacity, then, is the label for specific heat capacity tells you this definition. So it is joules per, or divided by, grams times degrees Celsius. So how much energy it takes for the mass of any object to go 1 gram of it 1 degree hotter. The table of specific heat capacities will be a table given to you. They're not numbers you need to memorize. Okay, so there'll be a thermochemical reference table where you'll get all these values from them. And this specific heat capacity is dependent on substance because really it's measuring kind of that potential again in the substance. Okay, some have a potential to need more energy to take its mass and heat it up 1 degree, and some need less. So if you think about it, to heat something up to make it move more, it's the mass of the particle that might affect whether it can move more easily or not, and then also the IMF, right, the force of attraction on adjacent particles. So when you look at this, some have pretty low specific heat capacities, mercury, lead, things like that. So that would mean that it doesn't take a lot of energy to get 1 gram of it and make it 1 degree hotter. But water, if you look at this list, wow, look at water. Water is 4.18, and it's one of the biggest ones on the table, apart from hydrogen. And again, this means that you need a lot of energy to take 1 gram of this substance and make it 1 degree hotter. And it's part of the reason why we use it to cool things off, because it'll take a lot of energy out of it to even change the temperature a little bit. It's also why we use it to cook, because per gram per degree, there's a lot of energy there available to use. Okay. It's also why on like a really hot day at a pool, from start of day to the end of the day, or from start of day to like the middle of the afternoon when it's really hot, the sun is really high and it's really hot, the like metal bar going into the water will be super hot, where like being in the day it might be cold to the touch and then it got super hot. Well, that's because its specific heat capacity is really low. It doesn't take many joules to make it hotter. But the water in the pool might not change that much, and that's because you need a lot of energy per gram per degree to actually heat it up. The other 2 variables that go into calculating the heat associated with a change in temp would be that change in temp, how much the temperature changed by, and the mass of the object. So the more mass you have of that object, the larger the heat energy, solely because you have more stuff, right? More potential for motion because you have more stuff. So to calculate the heat associated with change in temperature, it is mc delta T, the mass, times whatever the specific heat of your substance is, times whatever that change in temp was. So Q is another way to specifically talk about thermal energy. We talk about E being energy. Q is thermal energy in this case. So this is a way to quantify Q. Again, we can do endothermic and exothermic for this. If we end up with a negative Q, that means energy out. And that always happens when the temperature final is lower than the initial, because change in temperature is final minus initial. So if initial is bigger than the final, then you'll get a negative Q. Right? So essentially, and then the endothermic would be the other way. If you end with a higher temp than you started with, that's a positive Q. That's energy that went in to make that change happen. Now, the one thing to be aware of as soon as we do this endo and exo for this, you're used to thinking of endo as hot and cold, as we've already talked about. In this case, endothermic is energy in. Your final temperature will be higher for energy in, which means endothermic. And again, you're used to thinking of endothermic as cold. In this case, you're going to have a hotter substance because we are measuring, in this case, the system, and you are the surroundings when you say cold. So the gain in heat to the internal is the loss of heat from your hand, which is why it feels cold. We're going to run through 3 laws of thermodynamics now. Laws of thermodynamics would be laws, right, as it relates to heat motion. Right, so thermodynamics is the study of heat motion, and the Zeroth law is kind of like a math law, where like if you have 2 substances, A and C, and they're at the same temp, and you also have a substance B, and it's at the same temp as C, that means A and B are all at the same temperature. So essentially, the temperatures are equal if they're all in, if one is equal to the other is equal to the same one. So that's kind of like that math communicative property thing. The other thing is we're looking at something called thermal equilibrium. Okay, so thermal equilibrium is that moment where there's equal temperatures between 2 substances. So that equilibrium is always that moment when things are no longer changing. We might be transferring energy back and forth between our 2 substances, but the amount of energy changing is not creating a net change overall. So thermal equilibrium is when I end at equal temperatures. And if I'm at thermal equilibrium for 2 things and then 2 other things, they'll all be in equilibrium with each other, which means they're all going to have the same temp, because that's what thermal equilibrium is. The actual first law of thermodynamics, so not the Zeroth law, is the same law essentially as conservation of mass. Okay, in an isolated system, energy must be equal. Okay, energy lost by one has to be gained by another. So energy is never lost, it's simply changed around. And if you think about it even one step further, if like 10 joules of thermal energy was lost by one thing, that had to go somewhere, right? We always have a system and a surrounding. So if 10 joules was lost by some object, it has to be gained by another. So this first law is saying if I have something that loses 10, I will always have something that gains 10. So energy lost by one thing is always going to equal energy gained by something else. And technically, because of signs here, to make your energy signs correct, it would be the energy gained equals the negative energy lost to indicate direction, right? So it'd be 10 joules negative out by one equals 10 joules positive by another. So this is really exemplifying to you guys that negative is not a negative value like you're used to thinking in math. It is a direction. So my negative simply indicates to me that it was released, energy out. The second law of thermodynamics, we're only really going to deal with part of the second law of thermodynamics, is this right here. When 2 objects come in contact, heat will always flow from high to low temperature until you get to those objects reaching equilibrium. And again, what reaching equilibrium means is equal temp. So if I have something at like 25 degrees Celsius and something at 10 degrees Celsius, they will transfer energy from hot, 25, to cold, 10, decreasing the 25, increasing the 10, until they get to the point where they have equal temperatures, because that is what thermodynamic equilibrium means. It means equal temperatures. So if you combine the idea that if 2 things are equal and another 2 things are equal, they're all equal to one another in temperature, and the idea that energy lost by one thing has to be gained by another, and the idea that as energy flows, it goes from hot to cold until they're equal, we essentially can say that we can track delta H situations using Q equals MC delta T. So if I have a chemical reaction where there's a change in heat, and that heat is released into the surroundings, my surroundings are going to take that in, right? And my surroundings, given the certain situation, will increase in temperature because they took the energy in. And basically that increase in temperature, which I can use using MC delta T to calculate that Q, that would then be the delta H for that specific process. Okay, so given the fact that energy lost by one is gained by another, and the fact that they're going to transfer to one another, we can say that we can get delta H from an MC delta T situation. Okay, just by measuring change in temp, I can calculate the heat of the potential because that potential was released into a scenario where the temperature could change. It's a pretty advanced concept. We'll definitely do some math with that, but that's kind of all I want for background information for you guys. Come to class with this done, go ahead and do the form, and have a nice night.